Hello dear friends, glad to see you once again. Today we are discussing those 9 questions from Wave Optics which appeared for 2025 JEE Mains. Let me go to the first question without wasting time. Given below are 2 statements, one is labeled as assertion A and the other is reason as B. The first statement, if Young's double slit experiment is performed in optically denser medium than air, then the consecutive fringes becomes closer. That is the first statement. Second statement, the speed of light reduces in an optically denser medium than in air when its frequency does not change. So these are the 2 statements. Let's first of all read the first statement once again. If YDSE, Young's double slit experiment, is performed optically in a denser medium, in an optically denser medium, means a denser medium, than in air, then the consecutive fringes comes closer. This is true because you know the bandwidth is given by certain expression. Yes, beta, the bandwidth in YDSE is given to be equal to lambda d divided by small d. When you are conducting experiment in air, then lambda is lambda in air. But when you change the medium to some liquid or so, suppose you are replacing air with some liquid in YDSE, then the wavelength will get modified. If lambda is the wavelength of light in air, it becomes lambda dash in liquid. And you know that lambda dash in liquid is given to be equal to lambda by mu, where lambda is the original wavelength of light and mu is the refractive index of medium. So certainly, if you are conducting YDSE inside a liquid, then beta will be changed to beta dash. It will become beta dash is equal to lambda dash d divided by small d. That's a new expression for bandwidth. Now, since lambda dash is less than its original wavelength lambda, certainly beta dash will be less than beta. So the statement that in YDSE the bandwidth will be lesser is absolutely correct. That is what is in statement 1. If YDSE is performed in optically denser medium, then the fringes becomes closer is absolutely correct. So statement 1A, statement A I would say, that is a correct statement. Okay, what about the next statement? They call it R, okay. The speed of light reduces in air, then the consecutive, in optically denser medium than in air, while let me read it again. The speed of light reduces in an optically denser medium than in air. That's true. Because when a light wave changes its medium, let us say this medium is air here and it is some liquid or something like that on the other side. If a wave is passing from air to a liquid, something like this is noticed in the wave structures. You'll see that the wave is getting transformed into something like this. Certainly, you know that if it is c, the velocity of light here, the velocity v is smaller in this medium. So the velocity gets reduced, that's a fact. The wavelength is also reduced, you know, if lambda is a wavelength, it reduces to some lambda dash in the medium, that's a fact. And the frequency, you know, that will remain unchanged for a wave, no matter how many media it passes through. Frequency remains fixed, that will not change at all for a wave. So they are saying that when light is traveling to a denser medium, its speed will decrease, that's correct. Yes, the speed of light reduces in optically denser medium is right. So second statement is also right. I would say R is also right. Now, can you say that second statement is an absolute, is a good explanation for the first one? Yes, because when wave enters a denser medium, its velocity decreases. That is exactly why the wavelength decreases. And that is exactly why the bandwidth has decreased. So the second statement is appearing as a correct explanation for the first statement. So we must go with here option 2 because both A and R are true. Not only that, R is a correct explanation for A also. That's why we must go with option 2. Okay, so that was a question based on Young's double slit experiment. Okay, here comes 2. Given below are 2 statements, one labeled as again A and the other is reason R. Okay, another assertion reason question. In YDSE, the fringes produced by red light are closer compared to the fringes produced by blue light. That's statement 1. I think that statement 1 is absolutely wrong because bandwidth for any color, I can say, any light I can say is lambda d divided by small d. So when the color of light is red, you know that lambda for red in visible spectrum is much larger than lambda for blue or violet. Which color is that? They are calling it blue. Yes, of course this is true. When wavelength is larger, certainly bandwidth has to be larger. So lambda is larger for red light, and hence beta for red must be larger. So the result is that the actual result is that beta red will be certainly larger than beta blue. But statement 1 claims that for red the bandwidth is lesser, which is absolutely wrong. So statement A, yes, is a wrong statement. Okay, number 2. The fringe width is directly proportional to wavelength of light. That statement is correct because fringe width is directly proportional to lambda is a correct statement. So statement 2 is correct. I say the statement called R is correct. So first statement is wrong, second is correct. So you must go with option 4. Okay, I hope it is visible. Yes, that is it. A is false, R is true. Moving on to the next one, which is a numerical question, again based on YDSE. The width of one of the two slits in YDSE is D, while that of the other slit it is XD. If the ratio of the maximum to minimum intensity in interference pattern on the screen is 9:4, then what is the value of X? So this is YDSE conducted with slits of unequal widths. So when the slits are having unequal widths, they will be emitting waves of different amplitudes and a different intensity as well. Now here you are required to assume that the field strength is varying according to slit width. Field strength means amplitude. Okay, you can assume that field strength is a direct measure of amplitude of the wave. So when the second slit is X times wider than the first slit, then the waves generated from second slit will be having an amplitude X times that of the first wave or wave from the first slit. That is how they ask us to assume. Okay, let me tell you what happens here. Here, let's say that this is the slit. Okay, this is one slit. Sorry. This is supposed to be one slit. The other slit is much more larger in size. Okay, this is it. Okay, I hope you understood. This is one slit and the other slit is this. Now this is emitting wave, of course. Let us say amplitude is A for that wave. The second one, okay, this one is having a larger amplitude because the width of the slit is X times. So certainly the amplitude of this wave also will be equal to XA. So is intensity. When amplitudes are different, certainly intensity also will be different. But remember, intensity is proportional to square of amplitude. So when you assume that I is the intensity of this wave, certainly the intensity of this wave will be X squared I, because X times amplitude means the intensity has to be X squared times. So if we consider I1 as X squared I, then I2 must be considered as only I. So these are the intensities of the two waves as per the question, because they ask us to assume that when the width of the slit is doubled, exactly amplitude is also doubled. Okay, so when amplitude is doubled, certainly the intensity will become 4 times. They don't say double, they only say it is X time. So that's why it is X squared I. Now coming to maxima and minima, I'll remind you of all the expressions required here. I maximum, that means intensity at points where complete constructive interference is taking place. That's given by root of I1 plus root of I2 the whole squared. That's the expression. And I minimum is given to be equal to root I1 minus root I2 the whole square also. These are the equations of I maximum and I minimum. Let's put values here. I maximum here is root I1. Root I1 means, okay, this one. This is root I1, which is X squared I. So when I take a root, I'll get X into root I. This is root I1 plus root I2 means, okay, root I divided by, again, root I1 minus root I2, this minus root I. This whole squared is actually I maximum by I minimum. They ask us about the ratio of I maximum by I minimum. Okay, now that's said to be equal to, in the question it is said to be 9/4. The question is, what is X now? So let's simplify this. This root I is cancelled. I have X plus 1 divided by X minus 1 whole squared to be equal to 9/4, making it X plus 1 divided by X minus 1 as 3/2 when I take square root. Now cross multiplying, yes, I'll get 2x plus 2 is equal to 3x minus 3, which gives me, yes, 3 by 2. Of course, it is going to be 3x, yes, x is equal to 5. Simplifying this, you are going to get x as 5. So the numerical value of x is 5. Yes, you must go with option 2. That was question number 3. Moving on to the next question. It's again a question based on YDSE. The Young's double slit interference experiment is performed using light consisting of 480 nanometer and 600 nanometer wavelengths to form interference patterns. The least number of bright fringes of 480 nanometer light that are required for the first coincidence with bright images formed by 600 nanometer light is. See, in this case, YDSE is conducted using bichromatic light. They are using two light waves, two colors actually, to illuminate the double slit. So we must expect two different waves emitting from each slit. And you know, in that case, overlapping of bands will take place. Central bands will certainly overlap, and somewhere else exact overlapping will again continue. Now, to deal with overlapping of bands, you have an expression. Okay, I'll remind you that if n1 to bright band of lambda 1 is exactly coinciding with the n2 to bright band of lambda 2, then the coinciding will take place, or overlapping will take place in such a way that n1 lambda 1 equal to n2 lambda 2. Overlapping will take place at places where n1 lambda 1 is exactly equal to n2 lambda 2. So that's a condition for overlapping of two bright bands when you're conducting YDSE using bichromatic light. Okay, now it's a matter of only putting values. We are finding here what are the values of n1 and n2. Okay, n1 and n2 are unknown to us. Let's say n1 to bright band of 480 nanometer. So n1 into 480 is equal to n2 into 600 nanometer. That is it. So this, thereby you'll get the values of at least n1 and n2. Simplifying this, I'll get n1 by n2. Let me come to n1 by n2 using this. It is 600 divided by 480. Okay. What will be the least value? Okay, 12. It is 5 divided by 4. So when n1 is 5, n2 is 4. So let me just give you values here. Yes, for this n1, I can give 5. Okay, then n2 can be given as 4. So 5 into 480 is equal to 4 into 600. That is a condition for the first overlapping other than central band, which means that the fifth bright band of 480 nanometer will be coinciding exactly with the fourth bright band of 600 nanometer. That's how we deal with overlapping of bands. Now, what do they ask? They ask you the least number of the bright fringes of 480 nanometer to coincide with the 600 nanometer color. So the answer is 5, because it is a fifth bright band of 480 that is going to coincide. So it requires 5 full bands of 480 nanometer for this to happen. So your answer is 5. You must go with option 1. 5 is the right answer. Okay, that was 4. Coming to the next question in my paper, it's the 5th question, which is again based on YDSE. Young's double slit interference apparatus is immersed in liquid of refractive index 1.44. It has a slit separation of 1.5 millimeter. The slits are illuminated by a parallel beam of light whose wavelength is 690 nanometer in air. The fringe width on screen placed behind the plane of slits at a distance of 0.72 meter will be. So this is a question on bandwidth. Okay, bandwidth is given to be equal to lambda d by d generally. But here this experiment is conducted in liquid. So lambda must be replaced by lambda dash, where lambda dash is the wavelength of light in liquid. And you know that lambda dash in a liquid is equal to original wavelength divided by refractive index also. Okay, so let me write equation for beta dash in the liquid. It is equal to lambda dash d divided by small d. Now this lambda dash is equal to lambda by mu also. So it becomes lambda d divided by d, that into mu, because lambda dash is lambda by mu. Okay, let me put values. This is equal to lambda is given to be, let me come to substitutions now, which are the values. Yes, lambda is given to be equal to 690 nanometers. So 690 into 10 raised to minus of 9. Okay, that is lambda. That into capital D is given to be equal to how much? 0.72 meter. So directly in meters, lambda D by small d is 1.5 millimeter. Okay, 1.5 millimeter I can write as 3 by 2 into 10 raised to minus of 3. Okay, that into what is it? L. Yeah, it is refractive index is 1.44 also. Okay, 1.44. You can simplify this. Okay, let me simplify this 0.722. This becomes 2 times. 2 and 2 cancels here. Okay, it is 2, 3, 0, 10 raised to minus of 9, 10 raised to minus of 6. 230 into 10 raised to minus of 6 is what I get. Or I can say in millimeters it is 0.230 millimeters. So the fringe width in this experiment is 0.23 millimeter, which is that. Yes, it is option 1. Here is my next question. This question was slightly difficult, I think. Not much difficult, but still you must be aware of what is happening during polarization to solve it successfully. Okay, in YDAC experiment, 3 polarizers are kept as shown in the figure. 3 polarides, and they are P1, P2 and P3. Okay. The transmission axes of P1 and P2 are orthogonal to each other. That means they are mutually perpendicular. The polarizer P3 covers both the slits with a transmission axis at 45 degree to both P1 and P2. Unpolarized light of wavelength lambda and intensity I0 is incident on P1 and P2. Then the intensity at a point after P3 where the path difference of the light waves from S1 and S2 is lambda by 3. That's the question. So this is about interference. At a certain point there is an interference taking place. 2 waves are meeting after passing through all these polarides. Yes, let's begin with first of all what happens when unpolarized light is passing through this part. Remember, there is possibility of polarization here because this is intensity I0 falling on it. So this polarizer will certainly polarize that light. Certainly some light will come out. Okay, what is the intensity of that we'll soon decide. Similarly, when light is passing through, similar light is passing through second polaroid also, certainly light will be polarized. So these 2 waves coming out of the first polaroids are expected to be polarized light. Let's see what are the intensity of those waves first. So I'm talking about these 2 polaroids. So the first one is this, second one is this. Let me help you through certain diagrams. I'll just give you another view of this. Let's assume that this is the first polaroid. Okay, I'm just using a polaroid like this. Now believe that. Okay, I'll make it much more easy. Let's say this is the polaroid. I'm just giving it a circular shape. They don't say it a circular plate and all. Okay, I think that is more easy to illustrate at least. This is the way light is falling on the first polaroid, and it is said that it is unpolarized light I0 with intensity I0 that is falling on the first polaroid, let's say P1. Believe that the transmission axis of that polaroid is this. Then you know that polarization will take place, light will go to the other side. Now as it is a polaroid, you will see that light will have only vibrations in one single direction. That is what is polarized. That is what is called polarization. Now what is the intensity of that light? You must know. When light, ordinary light or unpolarized light is passing through a polaroid, you know, half the intensity is absorbed and only half the intensity is transmitted. So you must know that the intensity of this light emitting, emerging out of the first polaroid is I0 by 2. That was anyway P1. Now let me come to this polaroid. See, I'm talking about this polaroid now. Now that polaroid is having a transmission axis perpendicular to the previous one. So let me show a similar kind of polaroid in this figure. This is actually our second polaroid. Second polaroid has a transmission axis exactly for perpendicular to the previous one. So let me show that. Yes, this is the way light is coming. This light is unpolarized. It has vibrations in all directions. Again, I0 is the intensity. Now it is said that the second polaroid is having a transmission axis like this. This is actually T2. രണ്ടാമത്തെ polaroid transmission axis ഒന്നാമത്തേന് perpendicular ആണെന്ന് അവർ പറയുന്നുണ്ട്. So T1 and T2 are perpendicular. They are clearly mentioning that. Again, second polaroid also will emit light which is polarized. ആ polarized light intensity ഇതേപോലെ I0 by 2 ആണ്. But remember, the vibrations will be certainly parallel to the transmission axis. So these are the 2 waves coming out of the 2 polaroids, I1 and I0 by 2. I0 by 2 are the intensities. P1 and P2 are emitting lights or transmitting light of equal intensity. Pakshe, avരുടെ plane of vibrations are mutually perpendicular because ഈ രണ്ട് transmission axes are mutually perpendicular. Now let us come to the third Polaroid. ഈ രണ്ടും കൂടിയും രണ്ട് ലൈറ്റും കൂടിയാണ് ആക്ച്വലി ഈ പോളറോയിഡ് കൂടിയും അതുപോലെ രണ്ടാമത്തെ ഒരു പോളറോയിഡ് കൂടെ പാസ് ചെയ്യുന്നത്. ഒറ്റ കോമൺ പോളറോയിഡ് ആണ്. ഞാൻ വരയ്ക്കുമ്പോൾ രണ്ടെണ്ണം വരയ്ക്കുന്നേ ഉള്ളൂ. Anyway, that Polaroid is having a transmission axis which is making an angle 45 degree with the previous Polaroid. So let me come to the second Polaroid now. Remember, I0 is intensity here. ഇത് കഴിഞ്ഞ് പുറത്തേക്ക് പോകുന്ന ലൈറ്റിന്റെ intensity I0/2 ആണ്. Okay, let's come to the next Polaroid now. Let me show next Polaroid. ഒറ്റ Polaroid ഉള്ളൂ, ഞാൻ രണ്ടെണ്ണം വരയ്ക്കുന്നേ ഉള്ളൂ. I am showing the next Polaroid here. This is it. ഇതാണ് ആ Polaroid. അതേപോലത്തെ ആ Polaroid തന്നെയാണ് ഇവിടെ ഉള്ളത് because it's a bigger Polaroid. ഒന്നിച്ച് വരച്ചാൽ എനിക്ക് ഇവിടെ ഫിഗർ ബുദ്ധിമുട്ടായതുകൊണ്ട് ഞാൻ ഇങ്ങനെ വരയ്ക്കുന്നേ ഉള്ളൂ. This is it. Now this is the second Polaroid. They say that this Polaroid is making an angle 45 degree with the previous, when compared to the previous one. ഇതാണ് ആക്ച്വലി പഴയ Polaroid T1 എങ്കിൽ അതിൻ്റെ രണ്ടാമത്തെ ഈ Polaroid ഇത് P3 ആണ്. ആ P3യുടെ ട്രാൻസ്മിഷൻ ആക്സിസ് ഇങ്ങനെയാണെന്ന് പറയുന്നു. So let me call it T3. This is making an angle 45 degree with the plane of vibration. So certainly it will be emitting light, certainly with a lesser amplitude and lesser intensity. Now you know when polarized light is passing through a Polaroid, then resultant intensity is given by certain expression, which is I0 is equal to I into cos squared theta. That's the equation for finding the intensity of light transmitted by a Polaroid when polarized light is passing through this. Now here in this case, I for us is I0/2. That into cos squared 45 means cos squared theta means cos squared 45. Cos 45 is 1/√2, so you'll see that it is equal to I0/4 then. So the intensity of light transmitted by this Polaroid P3, which is through the first slit, light coming through the first slit is I0/4. Let's see what is the intensity of light emitted by the same Polaroid for the second slit. Yes, this one is I0/2. I come to this now, I0/2. That I0/2 is the intensity of light falling on P3. But remember, its transmission axis is the same. I'm showing that this is the same transmission axis. Yes, this is T3. Now that is making an angle 45 degree again because that is 45 degree. That transmission axis is making an equal 45 degree angle with the other plane of vibration as well. അതുകൊണ്ട് തന്നെ ഇതിൻ്റെ പുറത്തേക്ക് എത്തുന്ന light waves, okay, I'm showing that the light waves reaching on the other side will be having again a lesser amplitude, which is again given by the same expression. So this expression can be used here also. Now here also you'll see that theta is 45 degree. So the intensity of light emitted by this is also equal to as I0/4 because it is again 45 degree. So it is I0/4. In short, finally in the experiment you'll see that these two slits are emitting light of wavelength like this, intensity I0/4 and I0/4. This is how the light waves are finally transmitted through the Polaroid. Now let us address the real question. What do they ask? They are asking us to find the resultant intensity of these two waves, or at a point where these two waves meet, with a path difference of del is equal to λ/3. That's a question. So let's finally come to the answer. The question is about the resultant intensity. When two waves are having same intensity, then the resultant intensity at any point like this, I'm calling the resultant intensity as I dash. Resultant intensity is given by a simple expression which is 2I into 1 plus cos phi, where I is supposed to be intensity of each wave. This I mean intensity of each wave. Now here that I is equal to I0/4. So let me put values. Here it is 2I. I becomes I0/4 here. That into 1 plus cos phi. Now what is phi here? Remember, it is path difference, that is λ/3. If path difference is given, of course, phase difference is given to be equal to 2 pi divided by lambda, that into path difference. And here it is 2 pi divided by lambda, that into path difference is given to be λ/3. So the phase difference is 2 pi divided by 3. So the two waves are meeting at a point with a phase difference of 2 pi by 3. So it is cos 2 pi by 3 means cos 120. And cos 120 is equal to minus of 1/2. So substituting this we have 2 into I0/4 into 1 minus 2, which gives you 1/2. Yes, finally the answer is I0 by 4. So the resultant intensity at the point where the light waves meet with a path difference of lambda by 3 in this experiment is I0 by 4. Let us go to the next question. The ratio of power of a light source S1 to that of S2 is 2. 2 means 2 is to 1. S1 is emitting 2 into 10 raised to 5 photons per second at 600 nanometer. If the wavelength of light source S2 is 300 nanometer, then the number of photons per second emitted by S2 is what? So you are finding the numerical value that is missing in the answer. Okay, it's about power. See, if you assume that lambda is a wavelength or nu is a frequency of any wave, and assuming that light is traveling as a photon, I think I can give you the number of photons power relationship here. If h nu is the energy of one photon, then the power emitted by the source will be n times h nu, where n is the number of photons per second. H nu is the energy carried by one single photon. So if n number of photons are emitted per second, then the power is going to be nh nu, because power is a measure of total energy transmitted by the source in 1 second. So P is n into h nu. Now this question has wavelength also in it, so I can rewrite it as in terms of lambda. So power can be written as n into h c divided by lambda, where lambda is supposed to be the wavelength of light used. Now this question is about powers of two, I think two sources. So one source power P1 is equal to n1 into hc by lambda 1 for the first source. The power of the second source P2 is going to be n2 into hc divided by lambda 2 also. So these are the powers of the two sources. The question is about the ratio of powers. So let me come to the ratio now. P1 by P2. What is that? That's going to be dividing these two, will get n1 lambda 2 divided by n2 into lambda 1. It's over. Now given that P1 by P2 is 2 is to 1, this is given to be equal to 2 by 1 in the question. The question is, what is n2? What is the number of photons in the emitted by the second source? So n2 is going to be equal to, yes, it is n1 lambda 2 divided by 2 into lambda 1. It's over. N1 is given to be 2 into 10 raised to 15 photons per second. So 2 into 10 raised to 15. Lambda 2, the second wavelength is 300 nanometer here. I'm not changing units here because it's going to be the same lambda appearing in the denominator as well. Okay, that divided by 2 into lambda 1 is given to be 600 nanometer. So this is 600. Okay, so what is that? It's going to be 1 by 2. So this gives you some 1 by 2 into 10 raised to 15, or I'll say 0.5 into 10 raised to 15, that much photons. You want the answer in 10 raised to 14, otherwise it is 5 into 10 raised to 14, that much photons. So the answer is 5. 5 into 10 raised to 14, so the missing number is 5. You must go with 5 as the numerical value of the answer. So the answer is 5. Okay, going to 8. Next one. A double slit interference experiment performed with light of wavelength 600 nanometer performs an interference fringe pattern on screen with 10th bright fringe having its center at a distance of 10 millimeter from the central band. Distance of the center of the same 10th bright fringe from the central maximum when the light source is replaced by another source of light of wavelength 660 nanometer would be. So this is about the distance to some nth bright band. You must remember the standard equations. Remember, distance to any nth bright band in YDS is given by n lambda d divided by small d. This is the equation for the distance to nth bright band. Now this is about two different colors. So let me write two equations here. X1 for the first color is n into lambda 1d by small d. And in the second color, the distance to n, the same nth bright band, will be equal to x2. That is equal to n lambda 2d divided by small d, because only wavelength changes or everything else remains the same, because the slit separation, screen distance, they are not supposed to change in this question. Only the color of light is changed. Okay. Yes, x1 divided by x2. Let me come to solution. Now is lambda 1 divided by lambda 2. They ask you what is x2. x2 is equal to then x1 into lambda 2 divided by lambda 1. Now let me come to what is x1. They say that the initial distance for the first color was 10 millimeter. So that is 10 millimeter. I am expressing answer in millimeters, okay, 10 into. Lambda 2 is given to be 660 nanometer divided by 600 nanometer. Okay, the answer will get in millimeters here because it is 10 millimeter. Okay, this is going to give you some, how much is that, 11, yes, 11 millimeter. That is the distance to the new 10th brightband for the second color. Okay, that was not a difficult question, you know. Here comes the last question from wave optics. Which of the following phenomena cannot be explained by wave theory of light? Wave theory of light means classical wave theory of light. If you believe that light is traveling as electromagnetic wave, as Maxwell suggested, then there is one phenomenon that he can't explain with that theory. Sorry. The question is, which is that phenomenon? Yes, Compton effect, refraction of light, and diffraction of light. You know, reflection of light, refraction of light, diffraction, interference, everything can be explained using the classical wave theory of light. But phenomena like photoelectric effect, Compton effect, etc. cannot be explained by just assuming that light is a classical wave. You will have to apply quantum mechanics in order to understand what is happening in Compton effect and all. So Compton effect can be explained only by assuming that light is a photon and it has a dual nature and all. So classical theory of light will not help you explaining Compton effect. So wave theory of light fails, I would say, to explain Compton effect. So the answer is Compton effect. This cannot be explained using classical wave theory. That was the ninth question. So these are the 9 questions that we saw in our last 2025 JEE main exam. My dear friends, thank you for watching. We'll meet again. Take care. Bye.